Hi, everybody. This is Julia from the Massachusetts Public Library. We are back once again with science with Brian. Today he's going to be talking about exoplanets, and I'm getting out of the way. Yeah.
Okay. Hello again.
Hi, Brian.
Hi. It's our weekly session, it seems like.
Yep.
So I thought I would talk about exoplanets, partly because there's some things in the news about exoplanets, which is kind of an interesting comparison. But I'll start off with what an exoplanet is. We have planets in our solar system. Planets orbit the sun. And they're typically of a typical size. Like there's a little bit of debate about whether or not Pluto is a planet, and basically it's not big enough to be a planet according to the official declaration of astronomers. So last of the planets, but first in our hearts. But the basic definition of a planet is that it is a large enough body to be more round on its own weight, and it orbits the sun. And so exoplanets are planets that orbit another sun. They orbit another star because the sun is a star. And so when you find planets around other stars, those are called exoplanets, or out there planets. They were popularized by Carl Sagan back in the days of contact, when he speculated that perhaps every star will have a solar system of planets orbiting it. But when he talked about planets around other stars, we had not discovered any of them. We had no known planets around other stars until after he passed away. And interestingly, the first planets outside of our solar system weren't found around stars, they were found around pulsars. And that's because radio telescopes can actually measure the motion of a pulsar very precisely. And so that's how we were able to see that it's wobbling, so there must be some gravitational pull of a planet around it. It wasn't until kind of really the 90s, and then really after 2000 that we started finding planets. Because the telescopes are getting precise enough to observe the evidence of planets, typically in two ways. So if you look at the popular news, you'll see, possibly habitable planet discovered around some star. And a lot of times they'll have a picture on the front page, and it'll be this, Earth-like world with blue oceans and white clouds, and you can see the star, off in the distance. And that is a artistic rendering. We do not see planets in that way at all. In fact, we have not seen any Earth-sized planets at all. Even though we know they're there, we cannot see them. We can't see them with a telescope. We've seen a few, maybe a dozen planets that are large Jupiter-like planets around stars, and they look like a few pixels of a fuzzy blob, and we say, oh, that's a planet that we can see. So how do we know that there are planets going around other stars if we can't see them? And the way we find them is kind of two major ways. One is by their gravity, or the other is by their light. So the gravity method comes from the fact that if you have a star and you have a planet moving around it, the way we're typically taught is that all the planets orbit the sun, and that's a pretty good approximation. But what's actually happening is that as a planet's near the star, as it's orbiting, the star is pulling on the planet to keep it in its orbit. So the star's gravity pulls it to keep it in orbit. So the sun's gravity pulls on the Earth to keep the Earth going around the sun. But there's another part of that, is that as the sun pulls on the Earth pulls on the sun, because gravity works both ways. And so even though the Earth is really tiny, that means since the Earth is pulling on the sun is being shifted slightly. So if you have a planet going around a star, you can't see the planet because it doesn't give off its own light. It's not bright. What you're seeing is just the star. But if the planet's going around the star, then what you see is the star wobbles a little bit as the planet's going around it. And so the way we can measure that is that when we look at the light coming from the star, if the star is wobbling towards us or away from us, as it wobbles towards us, the light waves get kind of bunched up a little bit and they look bluer. They get blue shifted. And when the star wobbles away from us, then the light waves are stretched out a little bit and it's redder or red shifted. So what happens is if you watch the starlight and you see it get a little bluer, a little redder, a little bluer, a little redder, then you know that something must be orbiting this star. Now, the blue shift and the red shift are so tiny, we can't see it with the naked eye. So you can't look at a star and say, oh, that's bluer, or oh, that's redder. But what you can do is put it through a very precise spectroscope. And you can measure what the wavelengths of light are, and you can see it shift. So we can measure these shifts, but we can't see them with the naked eye. So that's one way. And because you use this color measurer called a spectroscope, that's called the spectroscopic way of finding planets. So you see the star wobble, and then you say, okay, there must be a planet that's gravitationally pulling on the star to make it wobble. And therefore, you know there must be a planet there. And what's nice is that if you measure that wobble, then what you can do is you can say, well, I know how big the star is, because I know what color it is and how far away it is. So I know what the mass of the star is. And if you measure the wobble, if you say, well, the amount that it's wobbling means that the planet must have this mass. So it's kind of like if you measured the wobble of the sun, you could figure out what the Earth's mass is. So when you use this color method, you can find out the mass of the planet. Now, I just used a simple one with one planet. You can actually do it with multiple planets. If there are 5 planets moving around a star, then you see it wobble in multiple ways, and you can actually plot out and go, oh, okay, so it's got one planet here, another planet here, and so forth. So you can find multiple planets by doing this, and you know all of their masses. So that's one way that we can find planets. That is actually the less common way. And it's less common because it's hard. There's an easier method that's called the transit method. And what you do with that is if you watch a star, if you have a planet going around the star and it happens to be lined up in just the right way, then what you can see is part of the light will be blocked. So for example, if this is the star and it's all giving off light, if the planet passes in front of the star, it blocks some of the sunlight, blocks some of the starlight. And so what happens is when we measure how bright that star is, we see here's the brightness and then it dims a little bit while the planet passes in front of it, and then it brightens again. And so you watch the star and you see, oh, there it dimmed a bit and then it got brighter. And then when the planet goes around again, oh, it dimmed a bit and it got brighter. And you keep watching the star over time. And when the planet passes in front of the star, you see it dim. The more it dims, the bigger the planet is. So if you use the transit method, you can figure out how big the planet is, like what its size is, because you know the size of the star, and then you know how much dims. And so if 1% of the star dims, then you know that the planet is 1% the size of the star. That one is a lot easier to do, particularly with a space telescope. So most exoplanets that we found have actually been found that way. So most of the planets that we have seen have been from this transit method. The only problem is it only works if the planet passes in front of the star from our point of view. So if you have the star here, here's your star, and the planet is in this weird orbit where it passes above and below and above and below, you're never going to see it because it doesn't pass in front of the star. So it's only if it passes in front of the star that you can see it. So when we look for these planets, there are lots of stars that we look at. We don't see any transits. We don't see it dim to show where there's a planet passing in front of it. That doesn't mean there isn't a planet there. What it means is there are no planets passing in front of the star from our point of view. So that's a limit that we can do. The wobble method is also a limit because the wobble method works best when the planet is kind of, again, in our kind of general direction. If the star wobbled like this, it would be really hard to see, and the color of the light wouldn't change because the color of the light only changes if it goes towards us or away from us. So you could have the star and it's wobbling back and forth like this, but it's light years away, so we don't even see anything. It's too small of a wobble for us to measure. So that, you know, has its own limitations. So those are kind of the two ways that we can do this. And probably in the past 10 years, we've put up a couple of space telescopes to look for exoplanets. And they use a nice little trick because they're using the transit method. But all they do is you put them up in space and then you point them in a certain direction where there's just a patch of stars, like thousands and thousands and thousands of stars. And you just point it there and keep watching all of these stars so that they actually have detectors so that they can watch thousands of stars all at the same time. They just watch them and watch them and watch them, and then they see when they dim. And so one of these was the Kepler telescope. And so if you look at a lot of exoplanets names, they will be Kepler something. And you'll say, oh, we've discovered the mass of Kepler such and such, Kepler 137a or whatever. And what that means is it was discovered by the Kepler telescope. So that's kind of the two ways that we find exoplanets. What's really interesting is that we went from, say, the time of Carl Sagan to having no known exoplanets. We only knew the planets in our solar system. To now, we have confirmed more than 4,000 exoplanets. We're discovering exoplanets so fast that now, like popular science things, it's like, oh, we've found more exoplanets. That's nice. You know, the exoplanet has to be special now for us to even talk about it because it's like, oh, this week we confirmed 5 more, and we confirmed a dozen more. Oh, well, you know, the numbers just keep going up and up and up. And there's a couple of new telescopes that are coming out or that are active. One is Gaia, which is actually looking at trying to map out where the stars are in our galaxy. But it's so sensitive that we can actually use it to find planets. And it just keeps finding planets as they comb through the data. And we're just finding more and more and more and more. And so even though we're still finding exoplanets, we now know enough about them that we know some interesting things. So we now know, based on statistics, that most stars have planets. Excuse me, sorry. That was my phone. I didn't turn it off. Most stars probably have planets. Based on the statistics of what we see, and knowing that we're only seeing the ones that are in the direction, we know that most stars probably have planets. The other thing we know is that our solar system is really odd. So when we look at our solar system, what we see is close to the sun, there are small rocky planets like Earth. So Earth and Mars and Venus and Mercury are terrestrial planets. They're small, they're rocky, they have nice solid surfaces. And then farther out, you've got Jupiter and Saturn and Neptune, and those are all gas planets. And so if you think about it, if you look at our solar system and say, well, actually, that kind of makes sense. Because as planets were forming, you would expect as the sun heats up, it would push away all the gas and dust from it. So any planet that's fairly close to the sun, all the gas and dust would be pushed away, and so they wouldn't be gassy planets. They'd be rocky planets because all the light, hydrogen, and helium and stuff would be pushed out. And the outer planets, well, that makes sense that they're gassy because that's where all the gas and dust would go. So that's where the large planets would be. And so when we were studying solar systems, we thought, well, probably our solar system is probably pretty common. Probably towards the sun, towards a star, you get lots of rocky planets. And then further out, you get lots of gassy planets. It turns out that's not what happens. It turns out that most stars actually have gassy planets close to them and not rocky planets. And we now know that what happens is that as large planets are forming, all the gas and dust around the star actually cause them to move inward so that they're closer. And so that makes our solar system unusual. So we have a nice cold Jupiter planet, a gassy Jupiter planet. A lot of stars have what they call hot Jupiters. These are Jupiter-sized planets that are close to the star, say the distance of Mercury. So it would be like having a planet the size of Jupiter where Mercury is in our solar system. And that's much more common. So why does our solar system look the way it does? And it turns out that probably there was some weird gravitational dance that caused Jupiter and Saturn and other gassy planets to move actually farther out. That they formed about where Mars is, moved in, and then because of some gravitational, what they call gravitational resonances, moved out, and that left room for the rocky planets. So it's like our solar system is really odd. So when people talk about habitable planets, we're going to find an Earth-like planet that's orbiting a star like ours. Well, it turns out that that's probably not going to be the common. That's not going to be very, very common. What's going to probably be more common is that if you have rocky planets close to the sun, it's probably orbiting a gas planet. So the most likely kind of habitable planets could be moons of Jupiter-like planets. So if you've seen the movie Avatar, for example, they go to another star system, and the planet that they land on is actually the moon of a gas planet. And so they actually made it that way because that could be really common. So that's one of the things that we find. The other thing we find is that there are a lot of planets that are the right distance from their star to have liquid water on it. When they talk about habitable planets or potentially habitable planets, all they know is that the planet is the right distance from the star that liquid water could exist on the surface. So if a planet is too close to the star, then everything's too hot and you can't have liquid water. It would just all boil away. And if you're too far away, then all the water would freeze and you wouldn't have liquid water. So if you say, okay, this is in the potentially habitable zone, what they call the Goldilocks zone, because it's not too cold and not too hot. If it's in the Goldilocks zone, it's potentially habitable. And people like to get really excited over that. But one of the things we know is that in our solar system, there are 3 planets in the habitable zone. Venus, Earth, and Mars are all in the habitable zone, and not all of them are Earth-like. So just being in the habitable zone, it could still be cold and icy, or it could still be too hot, or it could be too big, or too small, or all these other things. So even though there's lots of potentially habitable planets, then it doesn't mean that it's like Earth. But probably the most interesting thing about exoplanets in terms of like the statistics of them is if you kind of do the math and you say, okay, how many planets would there be in our galaxy, just in the Milky Way galaxy? how many planets might there be? And the answer is trillions and trillions and trillions. Just so many planets, they're basically uncountable. Habitable planets. There could be billions of habitable planets. Statistically, there should be billions of potentially habitable planets. So Earth, as a planet where life exists, there are billions of planets, probably, more than a billion planets in our Milky Way that are roughly Earth-sized and roughly in the right temperature zone that the Earth is from the sun. So there are billions of worlds out there that potentially could harbor life in the way that we know life on Earth. And so that's one of the kind of the biggest discoveries in terms of exoplanets, is that these are remarkably common. So when are we going to be able to see them? And how would we know if there's life on them or something? And that's actually a challenge that's happening right now. So finding exoplanets, well, that's kind of old hat. What used to be a huge discovery, and in fact, the first discovery of exoplanets around an actual star was given the Nobel Prize this past year. So that's Nobel Prize winning work. Now we have high school students that take an internship with some observatory, and they discover half a dozen planets. There was a high school student who had a summer project with NASA, and he discovered like 6 planets. It's so common now that it's like, yeah, just give it to the undergrad students and they'll find some planets. Just go look at the data and find us some more planets. Now, this is not uncommon. We used to joke about in school, some of our professors would say, as you do this hard experiment that's giving you such trouble, keep in mind 100 years ago, this would have won you the Nobel Prize. Now you have to do it successfully to pass the class. So, as it's easier, it's harder when you do it the first time. After 1,000 people have done it, it's not as hard. So planets are really, really common, but seeing planets is hard. And in fact, one of the recent things in the news is there is a star system, Beta Pictoris, that one of the first planets was discovered in this system. It's a very young system. It's got lots of debris, and it was like the first time where we could actually see a planet. There was big news several years ago about how we knew there was a planet there, and we saw a planet actually orbiting a little bit. It's like, wow, we have imaged this planet. Well, as they've gone back over the years and looked at the data, what we saw as a planet, it's not there anymore. So this planet that we had supposedly imaged somehow disappeared. What we now think happened was it actually wasn't a planet in the first place at all. What it was 2 asteroids that had collided, and they created this dense cloud of debris that was then so large it was the size of a planet. So basically all the rubble after it collided formed this kind of ball that was the size of a planet, and we could say, there's a planet. Well, then the rubble just kind of spreads apart and fades away, and then, okay, that wasn't a planet. So it's very difficult to do. But one of the exciting things is that in the next 4 or 5 years, there are a couple of telescopes that are going to come online that are specifically designed to see planets. So if we're fortunate, we should be able to see Earth-sized planets orbiting stars. Now, one, that's just cool to be able to say, yeah, you see that little fuzzy dot on the picture? That fuzzy dot is a planet the size of Earth. But it actually is very important for astronomers, because if you can see that fuzzy patch, you can analyze what the light is coming off of it. And you can do things like, okay, what is the temperature of the planet? Not how far away from the star is. What is the actual measured temperature? Because if you have light reflecting off of a star, it's also emitting kind of heat. So you can look at it with an infrared telescope and say, oh, it's giving off this much heat. Therefore, it must have this temperature. So we can say, is the temperature of that planet actually similar to the real temperature of Earth? Another thing we can do is we can look at light coming off of the surface of the planet. If it has an atmosphere, that atmosphere will absorb some of the light. And the colors of light that are absorbed are dependent upon what the atmosphere is made up of. So if we can observe these planets, we can say, oh wait, that planet is not only the right temperature of Earth, it also has oxygen in its atmosphere. It also has water in its atmosphere. That's when you get things start to get really interesting. Suppose we looked at a planet and we found the pattern of chlorophyll, which is what's in plants. That's a pretty strong case for life existing there. You know, so once we can actually observe planets and their surfaces, we can see not only what their temperature is, but what their oxygen levels are, what their atmosphere is made up of. If we observe them long enough, we might be able to see how the temperature changes, so there would be seasons. So all of these things that we could do, that's the next generation of exoplanets, to be actually able to see the surfaces. And these would be very blurry pictures, so they would not be the artist picture. You know, they would be like, okay, here's 10 pixels of a little smudge. That is a planet. But astronomers can get a lot of information from it, even though it doesn't look like a pretty picture. So that's kind of like the next step that astronomers are really getting excited for with telescopes like TESS and other ones that are looking for that. So it is revolutionized, and we're still radically changing our understanding of what exoplanets are.
Cool.
Any questions?
No, but once again, you made it something that I really didn't know anything about understandable and interesting.
Good. I'm
I
glad.
really appreciate it because, as I mentioned once before, science, I was a B student, let's put it that way, in science. So
Well, and a lot of science teachers don't make the effort to make it easy to understand. So
I know, and sometimes it's just not easy to understand. When
sometimes it's just not easy to understand. You're right.
Your brain is an English brain, not a science brain. So
I learned that many times when I try and write something and forget how to spell. So.
Yep. So that happens. That happens. Just like me with science. So thank you very much.
You're very welcome.
I liked your explanation about the gaseous planets and the rocky planets in our system and the difference elsewhere. That was very interesting. I didn't know that.
Yeah, I find that one very fascinating because I would have always typically said, you know, our planet is a typical planet around a typical star in a typical system, because throughout history, it's like, yeah, we're not special, but it turns out in this case, we actually are really unusual. So, do you have any ideas of things you want me to talk about in future
You
weeks?
seem to be picking pretty interesting topics as it
Okay.
is.
It's one of those cases where I don't know enough.
You know, I don't know what I don't know. So
right, exactly. I know that I don't know much of anything about science. So anything is always something for me to learn new.
Yeah.
Okay.
Even, I mean, an old dog can learn some new tricks. So that's why.
That's true. That's what I'm hoping for, because I'm still trying to learn things.
Me too.
Yeah.
About 20 years on you.
We're being homeschooled here.
Yeah.
Okay, well, that's good. I'll be happy to homeschool. I have a little bit of experience. Julia's got more experience, but I do have some.
So
good.
So bring us some more.
Right.
Okay.
Yep,
I will definitely do that.
Yep, we'll watch for them.
Okay, sounds good.
Thank you.
Thank you very much, and thank you to anyone watching it.
Yep.
We'll do this next week.
Yay.
Hope so.
Okay. Bye-bye.
Okay, bye-bye.
Bye.
Yep.